In previous lecture, we covered the design of the overfly wheel. Uh, Now, what are the limiting factors? Typically, the max stress is the one that's critical. So you want to look at the hoop stress as one of the ones that you want to look at. And usually the interference fit equation, if you have the same material, doesn't have to be the same material, but this is the equation you will use. The interference fit equation that you will use is that R equals A. So you will basically look at R equals A and then use this equation to figure out what the pressure should be at that interference. Remember, you usually know the shrinkage allowable. You know the modulus of the disk. You know the modulus of the other material. You know the Poisson ratio. You know the inner radius and outer radius. Sorry, outer radius and inner radius. So you know all this stuff, and you know also the spin speed. So because you know all that stuff, you can solve for pressure, P. And so that's a very straightforward thing. Why we don't move to some examples now, which is the purpose of this lecture. So for the examples, example number one, let me read the example for you. We have a compound cylinder shown below, and it's fabricated using, um, it's fabricated from a hollow outer cylinder and a solid shaft by using shrink fit process. So that's what the question so far. In this problem, there's no spinning here, but I want to kind of review that again with you to discuss a shrink fit process again one more time to make sure that's clear to you. Usually for these kinds of assemblies, there is a relationship between the shrinkage allowance, in this case, I'm calling it delta, and the interfacial pressure P. And usually that relationship will be given by P, the pressure between. So what is P again? Let me remind you what P is. P is a pressure between the steel material, which is the inner core, and the brass material that's outer core, the outer material. And so usually a relationship like that exists, and it has a linear relationship, and C is a constant. Okay, it was found that for a delta of 0.02 millimeters, the pressure that was found was 9.0 megapascals. And you may wonder how did they figure that out? You know, how they figure out that the pressure is that much. You can use methods that can measure stress using stress measurement techniques. You can use strain gauges that are installed on this material and this material to kind of back engineering what the strain could be, right? Um, that's one approach to be able to figure that out. And let me remind you what this delta of 0.02 really means one more time. So what does delta mean, right? What that means is the internal body of material, which is the core, is greater in size compared to the outside casing here, that's brass, by 0.02. Is bigger. So the thing I want to put in is bigger, and so I had to apply cold temperature, bring it in, and then let it come to room temperature, and that's causing a pressure. Can you envision what I'm saying or no? But that amount of difference is 0.02 is what this problem statement is saying, and they figured out somehow that the pressure is 9 megapascals, and I showed you in some ways how that can be measured. So the question is determine the radial and tangential stress at the intersection for both of the cylinders. So, okay, what is the stress right here is what they're saying. For either of those two materials, what is the stress there? That's what they're asking. And they give the Poisson ratio, they give the materials, allowables, and everything. So, well, the first step is to figure out what that constant C is. Well, I know what it is because P is 9 and delta is 0.02, so I know it's 450 megapascals. So I know what C is. I can determine that. And in the problem statement says the delta was increased to 0.1 millimeters. So they decided to change the process for some reason. They brought a new steel shaft, and they decided it needs to be a higher, even higher amount of allowance, shrinkage allowance. So therefore, the new pressure can be easily calculated. I know C from the previous equation here, 450, and I know that delta here is 0.1. So I can calculate the new pressure is 45. Pretty much done there. Nothing more to do there. I got my pressure that I needed. So now let's look at what that each of these pressures do. First, let's look what it does to the steel. And let's look at what it does to the brass. The pressure I'm talking about here, the 45, is between these two bodies of material. So I'm focusing on that line there, that interface that separates the outer cylinder and the inner core. So that equation is simple. I discussed that in the pressure vessel equations. This pressure is known, the internal pressure, PI. And so if I know PI, the pressure inside, and I know the internal radius and external radius, that's a very simple and straightforward calculation. The stress at R equals B, which is where I'm interested, can be easily calculated to be this much, which makes sense that the stress should be radially in compression because the hollow cylinder is getting compressed against that core. And it makes sense that the hoop stress is in tension because you have this reaction force occurring. What is going on with the shaft steel itself? Well, that's interesting. I can use the same equations I've been using for pressure vessel, but realize that the internal radius is 0. There's no internal radius. So that goes to 0. So you can see here A is 0 in this equation, in these two equations. But I do have an external pressure P naught, and the external pressure should be applied. I know what P naught is. It was 45. So I just apply 45. And you can see if A is 0, then B cancels. And then you get that the stress, radial stress and hoop stress in that material is 45. Doesn't matter where you're looking at the material. It's hydrostatic compression. That makes sense. It's getting compression in all directions by 45 megapascals. It makes sense that the stresses are also 45 megapascals in compression. That to me makes a lot of sense. Example 2. Any questions on example 1? Recording here for example number 2. Example number 2. I have a 0.5 meter outer diameter system, a 0.1 meter inner diameter system. So here, this diameter is 0.5, this inner diameter is 0.1, and then I have a 0.075 inch thick disc that's shrunk onto the steel shaft. So we're trying to figure out how to get it into the steel shaft. And we know that the assembly, this whole assembly is going to rotate at 6,900 RPMs. The first question that's asked, oh, and the material properties are given to you, Poisson ratio, modulus, and density. These units are weird, but that's the units of density to make everything work out nicely. So the first question is, what is the shrinkage allowance? Basically, what do we need to do to make this assembly work in the first place? So let's see how we tackle this. So the shrinkage allowance is, okay, and also note that the material properties for this system, they're both steel. They're not different materials. So I can use the equations I've been using for delta, the shrinkage allowance. So forget about omega, for example, for a second. ES and ED, the modulus of the different materials, is the same in this case. So that's why, but now I also have rotating speed as well being included. So, all right, okay. So for the wheel that's rotating, which is here, this wheel is rotating. I use the shrinkage allowance equation, which includes a spin speed. I have to because there's spinning going on. I cannot ignore that. So when I do that, I change the variable there, sorry, UD, but it's the same thing. I can easily insert here what the Poisson ratio is. I know what A and B is the radius of inner and outer radius. I know I'm calculating the deflection right at that boundary where the two materials meet. So that's 0.025 at R equals A, basically, the inner radius. And then I have rho, the density, and omega, the speed. So anyway, when you plug all that in, and I invite you to do it at home, in the comfort of your home, you get that the wheel rotating is going to produce a radial deflection of 0.0026 rho omega squared divided by E. But for the solid shaft, I can use pretty much the same equation here at the top, knowing that A is 0 there. So A is 0 because it's a solid shaft. There's no inner radius. So use the same equation. And when you do that, And you can see when A is 0, you get basically that equation. When you do that and you plug in all the numbers for that solid shaft, you get that the radial deflection is going to be this much. But at the boundary where we're looking at things, which is about here, at that boundary, we need to make sure, I'm trying to calculate shrinkage allowance. So it's going to be UD minus US pretty much. So when I subtract delta, so UD, the radial deflection for the wheel rotating is that, the solid shaft is US, subtract UD minus US to get the shrinkage allowance. And that way, you know, in real life, how to size or what temperature apply to get one material to fit into another, and then spin the disc so that things work properly. So that's example there. And now they're asking us to find the maximum stress. To find the maximum stress, you have to find first solve for the pressure when it's not rotating. So let's do it without no rotation first, and then we'll superimpose it later. So if you do have pressure, which we do in this case, and let's assume it's not rotating first, I just use the equations that have pressure in them. If you remember, let me go back to the equation so you can remember it. That's a shrinkage allowable equation. Omega 0 is not rotating, but the modulus of the materials are the same. So I can just use that equation for now. So I can solve for P, the pressure. And when you solve for pressure, that's the equation you get. A is 0 A is 0 because the inner core is a solid material, so you can remove A from here. And then you can calculate the internal pressure. Once you have the internal pressure, and that pressure I'm talking about is this one here, the contact pressure, where the hollow disc touches the core, the inner core that has no radius inside, right? So that's the pressure I'm interested in. Once I have that pressure, now just use the normal equations I was showing in 3 lectures ago, which is the pressure vessel equation. I apply the pressure to a thick cylinder, use the formula for that. I know PI, the pressure, 100.8. Plug it in there. I know B, I know A, calculate the hoop stress. So that's for non-rotating disc, right? That's for the non-rotating disc. I can then do that for the rotating disc. So this is for non-rotating disc. Now let's look at the rotating disc. So for the rotating disc, just look at rotating disc, but no pressure. Just no pressure, just rotating disc. That's the equation I gave you before. Calculate the hoop stress for that, and now you're golden. Now you take this solution and this solution and you add them up, because you can superimpose, right? So you have the pressure from the contact causing the stresses in the hollow cylinder, and then you have the spinning of the hollow cylinder causing more stress. So you take those two and add them up to get the total hoop stress that's occurring in the system. Is that clear? So again, analyze it in 2 pieces. First, the shrinkage allowance problem, and then 2, then analyze just the pressure alone with no rotation, and then analyze it with rotation but no pressure, and then add those 2 cases together to get the total stress due to the 2 conditions. Okay, one more time. Step 1, analyze it with no rotation, but with this pressure caused by the shrinkage fitting there. And then number 2, analyze it with no shrinkage allowance, just the rotation. Add those 2 together to get the superimposed conditions of the 2. And you can do that as long as the system is linear. Let's move to example 3. In example 3, I'm given a thick cylinder with closed ends, and I'm subjecting this to internal pressure PI. The pressure applied, they're asking to get the maximum allowable pressure PI if the tensile allowable is 140 and the shear allowable is 80. For that is a very simple solution. I know the stress in the axial direction, and I know the stress in the hoop direction. The stress in the hoop direction will be more critical generally, but these 2 stresses need to be looked at. I know the pressure. When I look at this here, there's no outside pressure being applied. There's no outside pressure being applied, so P naught is 0, so you can cancel that out. And I also already did it for sigma theta here. I already did that. Okay. So I'm ready now to calculate the pressures. And when I do, you can do those calculations. What you want to make sure is to calculate the pressure, the internal pressure, so that the stress does not exceed the allowable. You do that for the axial stress, and then you calculate the pressure that so that this hoop stress does not exceed the allowable as well. And finally, you will calculate the stress, the shear stress. The shear stress is basically 1/2 the subtraction of the two principal stresses. Or you can get the shear stresses on your own very quickly. In this case, we found this is the formula for shear stress. And what you want to make sure is you to solve for PI given the allowable of 80 that's provided here. And so you calculate the internal pressure for each of these equations. And then for the design process, you will actually take the lowest of all those pressures you calculated. There's three pressures you're calculating. One from here, the axial stress. One from here, the hoop stress. You don't want to exceed the allowable, right? And then you calculate the pressure for the shear stress, and you don't want to exceed the allowable. You calculate that pressure for those three cases, select the lowest because that's the most critical. And then if you're a good designer, you apply a factor of safety so that because you're not perfect, I'm not perfect, you apply a factor of safety. So say you calculate 50 megapascals, you divide that by 2 again, or a factor of 2. If it's nuclear, it's probably 3. You have to look at the application, right? If it's for an airplane, it's usually 1.5 factor of safety. If it's for rockets that has humans in there, it's 1.4. If it's not human rated, it's 1.2. Basically, it's just no humans in them, 1.25. That's a factor of safety. You apply that. So just giving a blueprint there, a lot of equations, but the important thing is to understand the concept, right? I can give you 400 examples, but none of them will make a lot of sense until you yourself do them. So I invite you to repeat the examples at home